This video is on applications of future value and accumulated present value. If you're in my course, you'll see this handout with the video. If not, you might want to pause it to write down things and then work through the examples. So the first thing, we're going to just recall a previous equation we used. It says to find the future amount in an account with interest compounded continuously, we use P of t equals P0 e to the kt power. Remember, this was, our exponential growth formula as well. So we use this when we have things that are compounded continuously. That's important. On the first example, we'll just kind of refresh how to use that. So it says find the future balance in an account after 3 years when $2,000 is invested at 6% interest compounded continuously. So, first thing you should notice is 3 years will be our time. The compounded continuously is what's telling us it's okay to use that formula. And we're looking for, the balance in the account. So we're looking really for P of 3. So what's P of 3? Well, P of 3 would be equal to P sub 0, which in this case, that's the initial amount invested, the $2,000. So we have 2,000 e to the k. What's k? K is going to be this interest rate as a decimal, remember, so 6% would be 0.06, right, for k. So e to the 0.06 times 3 powers t. And, that's the same as saying we have 2,000 e to the 0.06 times 3 would be 0.18 power. And then we can, take a look at this and see that it equals, on our calculator, 2,000 times second e to the 0.18 power. And we get $2,394.43. So we get 2394.43. And remember, this is money. This is how much money will be in the account if you leave it untouched after 3 years at a 6% interest rate compounded continuously. And, I could ask you how much you earned in interest. You would take this and just subtract off the principal, the $2,000. But this is something you should probably already know coming into this. The only other thing I want to point out is that when you're evaluating this, if your calculator does not display everything on the screen like mine, you want to, type in the exponent first, then exponentiate, then multiply by 2,000. So, moving into some newer material. So it says, if the yearly flow of money into an account is given by some constant function, which we'll call R of t, then the future value of a continuous money flow interest rate k compounded continuously over t years is given by. So it's given by this formula here, but let's talk about what this really means. We're saying the yearly flow of money into an account. So every year you're putting in, this is a constant function. So even though we call it a function R of t, it's going to be just a number every year. You keep putting the same amount in. Like if you put $400 every single year, that'd be like R of t equals 400. So it's saying if you keep putting in the same amount into that account every year, compounded continuously, the future value, right, of a continuous money flow. So when I say continuous money flow, that's what I'm really talking about. The continuous money flow is that every year I keep putting in the same amount. Interest rate k compounded continuously over t, capital T years, is given by this formula, A of t. So it's the amount after t years is given by the integral from 0 to t, the number of years, of R of t e to the kt dt. These lowercase t's are just our variable that we're integrating with respect to. You're not actually substituting in for these t's. It's part of the function. All right, you could have used x there. You could use any variable here outside of what you've already used in terms of capital T. So let's take a look at an example. So it says find the future value, that's tipping you off that you need to use this formula, of a continuous money flow of $800 per year being invested at a rate of 7% interest compounded continuously for 10 years. So continuous money flow is telling you that you should be thinking about using this formula here. If we were to talk about which pieces of the formula, you know, the 10 years, this is your capital T now. So when they're talking about this in a continuous money flow, we're talking about capital T. All right, so capital T is going to be 10 years. The continuous money flow, that's how much you're investing each year. Well, that's the constant function. This 800 is really the R of T. It's the amount that you're putting in each year into the account. And it's being invested at a 7% interest rate. Remember that it's going to give you K, which is going to be equal to a decimal. 7% of the decimal is 0.07. Remember, you move the decimal 2 places to the left. Or you could just say percent out of 100 and do 7 divided by 100 on your calculator. So our formula above, right, A of T equals, you know, the integral from 0 to T of R of T e to the kt dt. We're looking for A of capital T, 10 years, the amount in 10 years in the account. So the way I'm going to fill this in is the A of 10, and it's equal to, well, what's it equal to? It's equal to the integral from 0 to capital T, 10 years, of R of T, which we just said, that's the amount you're putting in each year, so it's going to be 800, e to the K, which we now know is 0.07, times T. Now remember, this T has to stay lowercase t, dt. It's the variable which we're integrating with respect to. It's, you know, it's a dummy variable. It's not what the function of. The function is going to be A of 10. It's of whatever you're substituting into it. So we want to evaluate this. Now, we should know how to evaluate this from earlier. Let's make sure you remember the integral here would be equal to, the 800 is a constant in front, so we can keep the 800 in front. Now you could pull that out to the very front of the integral, or you could just keep it in front as you integrate. So we have 800, let's integrate the e to the 0.07t. Remember, if you have e to the kt power, when you integrate that, it's e to the 0.07t, so e to the kt, same thing you have. And you divide by whatever the constant was in front of t, so you divide by 0.07. This is really kind of like undoing our chain rule. It's one of those rules that you should know for integration, though. If I have e to the kt power, right, the antiderivative is the exact same thing you see, and then divide by whatever was in front of t, so divide by 0.07. We're evaluating this from 0 to 10, remember? And then, you know, let's take a look at what this looks like when you substitute in. Well, this would be equal to, we would have, you know, the 800 over the 0.07. You might just want to write in front of the whole thing. And then I'll substitute in for t here. So, well, actually, before I do that, let me just show you what I'm doing. I'm taking the constants and I'm putting them in the front. You're allowed to factor those out to the front. And this would be 0.07t over 0.07. Right? We're going to evaluate it from 0 to 10. So now I'll substitute in, but the point being is I'm bringing the constants to the front, so I don't have to worry about them as I go through. And actually, sorry, I made a mistake here. Right, this 0.07 was pulled out with the 800. So it's 800 over 0.07, and then the e to the 0.07t will just stay where it is. So now taking a look at what we've got, this is equal to, I have 800 over 0.07 times, substituting in 10, we have e to the 0.07 times 10 minus e to the 0.07 times 0 power. And then we're going to want to evaluate this. So if I do that, you know, let's take a look at what this becomes. This is going to be equal to, we have 800 over 0.07 times, well, e to the 0.07 times 10 will be e to the 0.7 power, minus, this is, remember, this is going to be e to the 0 power, which anything to the 0 power is going to give you 1, right? E to the 0 power gives you 1. So e to the 0.7 minus 1. And you can use your calculator to evaluate this. So when you show work, I would like to see all of this. Once you're here, you can use your calculator to evaluate. Remember, we're trying to find its money, so we'll use 2 decimal places. And if I did 800 divided by 0.07 and then times, in parentheses here, I'll put e to the 0.7 power, close that parenthesis, minus 1, close the parentheses on that, and I get 11,585.745, so 0.75. So we'd have, our answer here comes out to 11,585.75. Remember, this is money, so this is dollars. So after 10 years, right, a continuous money flow of $800 per year being invested at 7% compounded continuously would give you $11,585.75. Right, so that's how much money you would have in the account after 10 years. Now, if you wanted to know how much you earned in interest, it's a little different than what we would do before, because you put in 800 per year, so you'd have to do 800 times 10, right, which would give you 8,000, and then subtract that off from here to get the actual amount of interest you earned. But so in evaluating this, you're always going to have the same type of integral, right? It's going to be a constant times e to the kt power. So you're always going to get that constant in front divided by whatever k is in front. And sometimes people can see that ahead of time. I still want you to show the step here, just making sure you understand how to integrate. Once you do this, I factored out the 0.07 from the denominator in the 800 and put it in front. You could have left it inside of here, but it just leads to more calculations you have to do. Remember, a constant can always be brought to the front of an integral. So we just factored it out to the front first, then we evaluated substituting in the upper limit minus the lower limit. Let's take a look at another example here. So for this example, we've got what should P sub 0 be in dollars per year, so that the amount of a continuous money flow at a constant rate over 20 years at 7.5% interest compounded continuously will be $50,000. So when they say what should P0 be, first off, continuous money flow, right? That's important. P0 is like they're really saying what's our R of t in the formula. Alright, so we're really looking to find what R of t is in our formula. This is so that the amount of a continuous money flow at a constant rate over 20 years, the 20, right, when you see this 20 years, that's telling you capital T, and this is at 7.5% interest compounded continuously. This, remember, is going to be k equals remember you're moving this 2 spaces back, so 0.0075. I'm sorry, 0.075. Right, because the decimal is there. So 1, 2, so it'll be 0.075. And interest compounded continuously will be $50,000. So what they're really saying is, what should R of t be, so that if I, invest for this amount of time at this rate, that I have $50,000 in the account. So this is your A of t side, the 50,000. So if you're thinking about the integral that we had set up, right, we had A of t, just showing the formula again, A of t equals the integral from 0 to t of R of t e to the kt dt. We're looking for R of t. We know what A of capital T should be. After 20 years, we want $50,000. So when we set this up, we're going to set this up as, 50,000 is equal to the integral from, 0 to capital T, so it'd be 0 to 20 of R of t, which we don't know what that is. That's what we're trying to find, which they call P sub 0, so I'll call it P sub 0 here. It's the amount that you're investing each year. So P sub 0, and then we have e to the k, which is 0.075. Remember, it's our interest rate as a decimal, so 0.075. And then remember, you need to still keep t in here as a lowercase t dt. It's our dummy variable we're integrating with respect to. Don't substitute in for that. If you substituted in the 20 into there, then you wouldn't have anything to integrate. It'd all be a constant. That wouldn't be the same thing. So we want to evaluate this. All right, so to evaluate this, we're going to look at this integral just like we did before, and we're going to have on the left side 50,000, stays 50,000. It's equal to integrating this, P0 is a constant in front, so I'll keep that as P0. Integrating e to the 0.075t, remember how this works, it's e to the 0.075t, divide by whatever the constant is in front of t, so 0.075. And then we're evaluating this from 0 to 20. Substituting in here, we have 50,000. We're allowed to keep the P0 out because I know it's a constant. If this was a function, you couldn't do this. You wouldn't actually be able to integrate it either. So that's why this needs to be a constant for whatever R of t is. So we have 50,000 is equal to P0. Substituting in, we have e to the 0.075 times 20 over 0.075 minus, substituting in 0, e to the 0.075 times 0 over 0.075. And we can simplify a bit. We get 50,000 equals, here we've got P0, e to the 0.075 times 20. You might want to do that 0.075 times 20 now, which gives you 1.5. So we really have e to the 1.5 divided by 0.075 minus, this is e to the 0.075 times 0, so that's just going to be e to the 0, which gives us 1 over 0.075. Don't cancel this, right? You need that term. And then simplifying this entire equation up here. So I have 50,000. It's equal to, we've got P0. Yeah, I'm going to factor out the 0.075 now. You could have done that way up here at this step if you wanted to. P0 over 0.075 times e to the 1.5 minus 1. That's just need to factor out the 0.075. Remember the goal. The goal is to solve for P0. Well, how would you do that? Well, to get rid of the fraction, you would multiply both sides by 0.075, right? And then you want to divide by this e to the 1.5 minus 1 because you want to isolate P0. So you'd have really 0.075 times 50,000, right, if I multiply both sides by 0.075 here. And it equals P sub 0 times e to the 1.5 minus 1. And then, we can evaluate that if you want. 0.075 times the 50,000. We get 3750. So you have 3750 equals P0 times e to the 1.5 minus 1. And then, like I mentioned, you want to divide by this e to the 1.5 minus 1. I divide by what it is as an exact value. So we're dividing by e to the 1.5 minus 1. So we get P0 equals. Now, when you divide this in your calculator, make sure the denominator is in parentheses. So you have 3750 divided by, and then in parentheses, e to the 1.5 minus 1. Oh, close the parentheses on the 1.5, and then minus 1. Close the parentheses on the whole denominator. I've got 1077.06. So 1077.06. Remember what this is. This is dollars. It's the amount per year you should be investing now into this account for 20 years. So you invest this amount, $1,077.06 per year over the 20 years at a 7.5% interest rate. So you'll have $50,000 in 20 years. All right, so when you see these formulas where you have, this continuous money flow, investing a certain amount over time, all right, you want to use the formula that we had here for the future value. The next definition, we talk about the accumulated present value. All right, the accumulated present value is something different, right? So the accumulated present value, A, of a continuous money flow into an investment at a rate R of t, dollars per year, from now until t years in the future is given by this. Since A equals, it's really the same formula, right? A equals the integral from 0 to capital T of R of t e to the negative kt dt. The only difference is that the k is negative, right? So the difference in the formula is that you have a negative on the k, but when you do it, it's based on what the question's asking you, because the questions we just asked a minute ago, we used a positive k. Here we're using a negative value for k because we want to know really, right, and this is what I'm putting in the quotes here, because this is really the way you should think about it. It says this gives you the amount you should invest now rather than investing continuously to have the same amount after T years. So this A is not the amount that you're going to have in T years. This is the amount that you should invest now so that you could have the same amount as if you were to invest continuously over the time. So let's take a look at an example. So for this first one, it says the accumulated present value. And these words, accumulated present value, are telling you to use the second formula. Over a 5-year period, that's your capital T, right? 5-year period. So over a 5-year period, if there is a continuous money flow of $2,400 per year at a rate of 14% compounded continuously. So let's take a look. So accumulated present value is telling you to use this formula here. You know, everything else about this is going to be the same. We're trying to find the amount, right, the accumulated present value, the amount that would be equivalent to, if you, like the amount you would have to invest now, that would be equivalent to if over a 5-year period you were investing $2,400 per year at 14% compounded continuously. So if we're substituting into this, right, the formula tells us we have A equals, and it's the integral from 0 to T. So it's 0 to capital T, or capital T is 5 in this case, right? It's the number of years, so 5 years. Of R of T, remember R of T, right, that's the amount that you would invest continuously. Well, what did that tell us? The continuous money flow is $2,400 per year. So this would be 2,400 e to the negative kt. Well, what's k going to be? Well, if it's 14%, it's going to be negative 0.14. The negative, because the formula has a negative. And then make sure you have the lowercase t dt. Remember, that's the variable we're integrating with respect to. Don't sub 5 into there. And now we want to take this antiderivative. And if I do that, all right, we have A is equal to the 2,400 can stay in front as a constant. And integrating this, e to the negative 0.14t, remember how this works, e to a constant times t, you write exactly what you see and you divide by whatever that constant was in front of t, so I'm dividing by negative 0.14. Make sure you have the negative sign on that. And this is going from 0 to 5. And then we can bring our constants to the front. So this will equal 2,400 over negative 0.14 times e to the negative 0.14t. We're evaluating that from 0 to 5. So I'm just bringing the constants to the front like I did earlier, just to make it easier to work with. This is going to be equal to, maybe I'll do it down here just to give myself a little more space. This is equal to 2,400 divided by negative 0.14 times e to the negative 0.14 times 5 minus, substituting in 0, e to the negative 0.14 times 0. So this equals 2,400 over negative 0.14 times e to the negative 0.14 times 5 will be negative 0.7 power minus e to the 0 power here, which will be minus 1. And then we can evaluate that watching your negatives when you type this in. We have 2,400 divided by negative 0.14 times, in parentheses, e to the negative 0.7 and then minus 1. Close those parentheses up. And I got $8,629.96, and there's an extra 6, so 97 cents. So when we go to write this out here, we have, this is $8,629.97, rounding to the nearest cent. And let's make sure we understand what we found. It's really saying if I invested $8,629.97 now, right? Just a one-time investment for 5 years at 14% compounded continuously, that would be equivalent to the same amount that I would get if I invested $2,400 per year over the 5-year period. So that's what I'm really finding when I say this 86, 29, 97. Now we'll check this. I just want you to see like why this is true. So I'm saying this is when they say accumulated present value, they're saying this, what amount would you have to do as a one-time investment now to have the equivalent of what you would over that 5-year period at the same interest rate. Let's take a look at what this would be in terms of how we would use it. So if I was looking at this, we know that the compound interest formula, P of t equals P sub 0 e to the kt is our normal compound interest formula. So if I was just investing now, I'd be investing the 86, 29, 97 we just talked about as my P0 right away. And we're going to be doing it for 5 years at 14% compounded continuously. So we're gonna verify that what I said is true. So I'm really looking for P of 5. P sub 0 would be 86, 29.97 e to the k, which we know is 0.14 because it's 14%, times 5, so times t power. And if you do evaluate this on your calculator, you should know how to do this. This is old news, but it's really showing us what we just did. So if I do 86, 29.97 times second e to the 0.14 times 5 power, just times the 0.75, I get, this comes out to $17,378.63. All right, so this is, if I was just going to do a one-time investment. All right, so this is what this is, one-time investment on this side. On the other side, I'm going to talk about, okay, what if I was to invest the $2,400 per year? Well, now we're using the formula from earlier where we talked about A of capital T, right? The future value. A of capital T, remember, was equal to the formula from 0 to capital T of R of T e to the kt dt. And when we talk about evaluating this, remember we're looking for A of 5. And this is going to be the integral from 0 to 5. R of t, now they're saying that what we wanted to do is find the equivalent amount to what if we invested $2,400 per year. This would be 2,400 e to the k, which is 0.14 t dt. And we'll evaluate this. Well, what's this come to? This ends up being, right, this 2,400 is a constant in front. Integrating e to the 0.14 will be over 0.14 e to the 0.14 t. What I'm really doing is taking the antiderivative of this, e to the 0.14 t, and dividing by the 0.14. And we're evaluating this from 0 to 5. You can put your constants in front. I'm doing it a little more quickly here just to save time, just to show you the values come out the same. So evaluating this, we have 2,400 over 0.14 times e to the 0.14 times 5 power minus substituting e to the 0.14 times 0 power. This comes out to 2,400 times, or divided by 0.14 times e to the 0.7 minus 1. Right, because e to the 0 power is 1. And then calculating this, if I do this, we got 2,400 divided by 0.14 times, in parentheses, e to the 0.7, and then minus 1. And I get, when I evaluate this, we have $17,378.61. That's 7 around at 0.62. So this is what we would have gotten if we invested $2,400 per year for 5 years at the interest rate of 14%, right? This is what we got if we invested the 8629.97 just one time at an interest rate of 14% for 5 years. And you can see that they're essentially the same value, right? It's off by a penny. But the point being is that this is what we were finding when you found the accumulated present value. You were finding the value that would make these equal to one another. So when I say make these equal to one another, what I'm really saying is if I invested $8629.97 once, that's the equivalent of investing $2,400 every year for 5 years. All right, the next example has to do with consumption of natural resources. It actually uses the same formula we've been talking about. It says here, suppose that P of T is the annual consumption of a natural resource in year T. So, you know, we're really talking about every year a certain amount of a natural resource is used, you know, like 500 tons per year. If the consumption of the resource is growing exponentially at a rate K, then the total consumption of the resource after T years is given by this formula here. And it's the integral from 0 to T of P sub 0 e to the kt dt. So natural resources are typically consumed in the same way each year. And what it's saying here is that, you know, if it's exponential growth, we use this formula here. So in 2000, all right, and they're telling us use T equals 0, all right, is the year 2000. The world gold production was 2,457 metric tons and growing exponentially at a rate of 0.6% per year. So the gold production is what we're talking about here. It says if this growth rate continues, how many tons of gold will be produced from 2000 to 2013? So when we look at this, first thing you should recognize is that, you know, 2000 is, you know, when T equaled 0. They told us that. In 2013, well, that's telling us that capital T equals what then? Well, it's 2013 minus 2000, so it'll be 13 years. And so we're going to use the formula they have above, right? So this is going to be the integral from 0 to T, which is 13. Right, capital T is 13, of P sub 0. Well, P sub 0 is the amount, right? It's the initial amount every year. Well, they're telling you what it was. They told you this 2457. Right, so you're going to put 2457 here. Right, that's, you know, like our P sub 0 has always been like the initial amount. Right, so when you see that, that's your P sub 0. And then e to the kt. Well, it's e to the k, which is, we got 0.6%, so be very careful here, right? So 0.0, right, moving this over 2 places is 0.006 is what we use for K. So this will be 0.006. So this is e to the 0.006. Remember, lowercase t dt stay in there as is because remember that t is our variable of integration. And then when we look at this, now we're ready to evaluate, just like we did in the earlier examples. So looking at what we have here, we've got this integral. The constant can stay in front is 2457. And then we have e to the 0.006 t power. Remember, when you integrate e to constant times t, it's the exact same thing you see divided by the constant in front of the variable, which would be 0.006 here. And we're evaluating this from 0 to 13. Once you have that, remember what we're doing. We're going to factor that constant to the front just to make it easier to work with. So we'll factor out 2457 over 0.006. Remember, these don't have variables with them. That's why you're allowed to bring them to the front. And then e to the 0.006t, we're evaluating from 0 to 13. We'll substitute in here. So we got 2457 over 0.006. Remember, upper limit first, so it's e to the 0.006 times 13 minus e to the 0.006 times 0. And we know that this is equal to 1 for this last term. So we've got this whole thing equals 2457 over 0.006 times e to the 0.006 times 13. If you wanted to multiply that out right now, you could. 0.006 times 13 would be 0.078 minus, remember we said e to the 0 power is going to give us 1. Make sure you don't just cancel it to a 0. You need that 1 there. And then we'll evaluate this, and we get, multiplying this out, 2457 divided by 0.006 times, in parentheses, e to the 0.078 power, close the parentheses on e, and then subtract 1, then close the parentheses for the multiplication. And we end up with, we got 33219.712. So we've got 33219.728. So we got 33219.728. So 0.73. And let's make sure we know what we found here. This is the number of what? Well, this is the number of metric tons, right? This is the how many tons of gold. So this is the same units as the 2457, so metric tons. So what it's really saying is that in 13 years, right, they're going to produce, over that entire time, 33,219.73 metric tons of gold. So it's telling you how much is consumed, how much of the gold in the world is consumed in the 13 years from 2000 to 2013. Part B, it says the world resources of gold in 2000 were estimated to be 77,000 metric tons. All right, so when t equaled 0, right, in that first year, they estimated that 77,000 metric tons were estimated to be left. How much resources we had left of gold? 77,000. Assuming the same growth rate of 0.6% per year, when would the world's gold resources be depleted? So when we talk about this, you know, what we're really saying is that we're trying to find capital T, right? So what this is really saying is, you know, what is capital T when I say when? All right, they're telling us how much is going to be used up. They're saying when will be depleted means when all 77,000 metric tons are used. So how many years will that be? So we're going to use the same formula, right? We're really going to use the formula that we had from above, the integral from 0 to t, except for I don't know what capital T is. So we're doing the integral from 0 to capital T of 2457 times e to the k, which is going to be our 0.006 lowercase t dt, and we want to find when this equals 77,000. Right, so what it's really saying is, you know, what's the t value, capital T value that causes this to become 77,000? Well, what we're going to do is we're going to integrate this. We're going to keep capital T in there as a variable because we're going to solve for, and then we'll solve this equation. So solving this here, integrating the left side, you'll have 2457 e to the 0.006t would be the integral of that is e to the 0.006t, and then remember you divide by 0.006, and this integral we're evaluating from 0 to capital T. We know it should be equal to 77,000. And then, you know, you want to do what you normally would. We can factor the constants to the front, so I can have 2457 over 0.006 times here. Looking at this, right, you've got e to the 0.006t. I'm going to substitute in as we go. I think we've done enough of these now that you understand that this would be times the e to the 0.006t, and then with the limits of integration, subbing in the upper limit would be e to the 0.006 capital T minus e to the 0.006 times 0 equals the 77,000. Simplifying here, we have 2457 over 0.006, and then this is times e to the 0.006, capital T minus e to the 0, remember, is going to be minus 1, equals 77,000. Now remember the goal is to solve for capital T. If I'm trying to solve for capital T, make sure you know how to solve this. It might not be obvious to you. You want to remove this fraction from the front here. If you did, you know, we could do this by dividing first and then, you know, working out what that value would be. If I divide 2457 by 0.006, 2457 divided by 0.006, I get 409,500. So 409,500 times, we have e to the 0.006 capital T minus 1 equals 77,000. And to solve this, first I'll divide by this 409,500, because really the goal is to get capital T out of this exponent, and I can't do that until I isolate the exponential. So we're going back to solving methods we've used in the past. So you're going to divide by 409,500, or 409,500 to each side. This gives us e to the 0.006 capital T minus 1 equals, I'll leave this as 77,000 over 409,500 for now. And now remember, you're going to isolate the exponential, so I'm going to add 1 to each side. So I have e to the 0.006 capital T equals this, 77,000 over 409,500 plus 1. And remember, you're going to take natural log of each side now to get that exponential out of there. So we have the natural log of e, or I'm taking the natural log of this, equal natural log of this, take the natural log of each side. This gives us 0.006 capital T. Remember why we did this, right? Natural log and e are the same base. When you take the log of the same base, an exponential of the same base, it's just the exponent. So you have 0.006t equals natural log of 77,000 over 409,500 plus 1. And then to solve, you'll divide by 0.006. You divide by 0.006. And we have a capital T equals, I'll do this on the calculator here, be careful with your parentheses. You have natural log of 77,000 divided by 409,500 plus 1, close the parentheses, then divide by 0.006, and I get T equals approximately, I'll use 2 decimals here, 28.72. 28.72 what? Well, T was measured in years, right? It was years when? Years since, you know, T equals 0 is 2000. So 28.72 years after 2000. Alright, so T is equal to 28.72 years after the year 2000. So when they ask you when would it be depleted, you know, they might say round to the nearest year. So if we rounded that up by 2029, right, we will use all the gold in the world if we're using it at the current rate of, or the rate in 2000, which was 2,457 metric tons. So if they're mining gold at that rate, after that amount of time, you know, there wouldn't be any gold left. We would have used it all up. You know, it would exist, but we wouldn't be able to get any more of it. Hopefully, you know, the examples in this section helped. You know, the ones for future value and accumulated present value, you know, have similar formulas, but they are different. The consumption of natural resource is really using the same formula as the future value, as we talked about earlier for the money problems. So make sure you do practice this, you know, and make sure you are looking at the words in the problems, right? If it says future value, right, you're using this equation here. If it says accumulated present value, you'll be using this equation here with the negative in it. So the words matter, right? So accumulated present value means the amount that you'd have to invest now to have the exact same amount as if you were to invest yearly, at a constant rate. Future value just means, how much will be in the account after that amount of time. So hopefully it's helped.